So, so far, we have done some of the topics in the multiple integrals. The first part, the double integrals, the Fubini theorem, and then we have the integrals or double integrals over general regions, which is basically we have or we need to describe the curve in the endpoints of the integration can be described either function of x or function of y in the double integrals, and basically that's it. And there is one more thing on the double integral that I need to emphasize. This is the topics today. So I would like to start with the change of the order of integration. So change of order means we are going to change the order. So suppose we have this dy dx, and if we have this sine y squared dy dx, if we are going to integrate this, if you could try, can you integrate this? All right. The short answer is no. You cannot do it directly, or sometimes there will be some double integrations that when you look at the inside integral, it's not so easy to integrate. So to solve this problem, one way to overcome is to change the order of the integration. Because if we are going to change this becomes dx dy, the sine y squared can be integrated easily. If this is integrated with x, we could just multiply by x, right? Because y is we treat as a constant partial, right? So then how do we change the order? Okay? Because if we change this dy and dx, there will be some problem within this, right? In the endpoint. If it is a constant, it's no problem. We can use the Fubini theorem, no problem for dy dx if we change the order. But if this has happened in, for example, it's happened within the general region in which we can have a curve on the endpoints. Okay, so first, if we decide to look at the endpoints, for example, we have x that is a constant, but for y it's a starting from x okay, that's what we have. So it's a line. So we could write this as like that, which means if we want to change up the order, it would be better if we draw the area, okay, the area of the endpoints, okay, the restrictions. So first is we are going to take the constant, which is start from x equals 0 to x equals 1. Let's say this one is here, okay, and maybe the other one will be here. Okay. So we start taking x from 0 to 1, but then we have y equal x and y equal 1. That's our another endpoint in 1. So y equal 1 is this, right? I think we can draw a line on that part. So I think I can just draw like this and say that this is y equal 1. And then y equal x is just a line like that, right? Okay, agree. Y equal x. So then the area that we want to integrate is this. Okay. So I think I can draw. Suppose that this is y equal x. Okay. So there are several possibilities. Okay, depends on the endpoint. It could be this triangle. It could be this triangle. Okay, it could be. Okay. Not proportional. Let me make this
maybe change this to, okay, maybe that will be better. So this will be precisely going 1, okay? So this will be our area D.
And we can confirm, okay, it starts from 0 to 1, okay, for x, and then for y, it starts from this and that. Okay, so it starts from this and that, that will be the area. Okay. So this is the area for that endpoint. So if we change the order of the integration, what we are going to do is we are going to make y as our constant. So we are going to take 0 to 1 for y.
Okay. So we can write alternative description of D is, we can start taking that.
So if this is a constant, then what will be the x? The x start from, we need to make sure that this is D. Okay, this is the area that we want to evaluate. So we need to start, now it's x. X equals 0 until x equals y. Okay, you get it? If you start from x equal y to x equal 1, you end up with this triangle. Do you see it? Okay. So we need to start with x equals 0 and then ends up with the x equal 1. Okay. So that we can have this as our restriction area, okay, the endpoint. Okay.
So this will be start from 0, x until y. So we could write down the so change of order. So let me write the question is 0, 1, x1 sine y squared dy. Yeah, so this will be equal to 0, 1, and then 0y sine y squared, and then this will be dx dy. Okay, now when we change this order,
now this will be possible to evaluate with the integration. So sine y squared is
become x, so we can and then we can input the y. So this will be y sine y squared dy. And then from here we can take substitutions. And this will be half sine u du, and 0, 1 is still the same if we square, so 0, 1, so half of cosine u from 0 to 1, half cosine 1 minus 1. Okay. Oh wait, should be negative here. Or if you want to multiply, it will be 1 minus cosine 1. Okay, so that's the idea of the changing the order of the integrations. Of course, how do we able to change the order? It's based on the endpoints. How do we construct in the diagram or in the graph? And then you need to understand the visuals. If you don't understand how do we get this from this questions to this, will be very hard. It will be very. Sometimes maybe the question is asking to this part. The more you struggle for this, okay, unless you are able to change the order, you will not. You won't be able to solve this. Okay? Well, unless if you maybe compute with some numbers, maybe you can. But this is a curve. Okay? So it's not something that you can solve in calculator. Well, perhaps the Wolfram Alpha can. You try. But for your calculator, it's not possible to solve that. Okay. Any questions about this? Okay. Maybe more exercise, but I think I will prepare exercise for this part later on. Okay, maybe next week. I think we can continue for a while. I'm preparing actually for today's class. I'm optimistic we will move to the next part, but I think I will stay for a while within this part. There are some property in double integrals. Okay, the first one is we can split the endpoints. Okay, that's I think very similar to the regular integrals. So integral in calculus 1, we can split the area, right? We can also split the d. Okay, we can split the d. So suppose that we have two functions. So we can split this with the same d. We can split become each one of the double integrals. And then it's not actually, this is supposed to be here. So we can split, and to be precise, we can split also the d. So we can split the function, and then we can also split the d. Okay, so split become d1, and then plus d2. Oh yeah, already right here. Okay. And also, if you have a constant, you can also factorize the constant. I will just write this here. Just like a regular integrations. Okay, so I think not really a big deal. Okay, so basically you can split the area. Okay, the other important property is if we have the function of the surface is just 1, okay, over region D. So we get the area of the D, which is the double integration of that 1 dA, which is actually the area. So in terms of the application, we can also apply the double integral for more. So basically, functions of two variables equal a constant or equal 1 here means that this will be the plane at z-axis cutting z equal 1. So here, so that we have the height of the volume of our shape here is precisely 1.
So basically when we multiply with 1, it's actually the same thing as it is, right? So the base multiplied by 1 is the base itself. So basically we are getting the area itself. Okay? So that's why we have the area. So we can apply the double integrals to compute the area. And then from this volume, we can then have some comparison theory. Okay, so let me continue for a while. So the next part is this theory here. So if we have the, let me write here, we have two plane. So we have the small m, we have the capital M, and our surface is in between these two. Okay? So this blue curve or blue surface is our function, and the function is in between this m, okay? between small m and capital M. Okay, so using the double integral, when the function is in between those m, we can take the double integral, and this value will be between the m area of D and also the capital M area of D. So it's in between. So what is the purpose? Why we are doing this? This is, I believe, is good for estimation. It's good for finding error. It's good also for analysis of some functions. Okay, if you know how much functions can be maximized and how much function can be minimized, and you know the function couldn't maybe move forward or move downwards, so it's always in between some certain value, so we can estimate how much we need to evaluate. So if we want to, for example, estimate this double integral e with power sine x cosine y, this is something that is not easy to be evaluated. Okay, so sometimes we need to measure by taking some approximation. So basically we need to make some assumptions. So based on this, based on the trigonometry, we have some basic idea that the sine and cosine, they will have their own minimum and maximum value, right? So when we multiply these two, of course there will be some combination between these two. So there will be, at least the minimum should be -1, maximum should be 1, okay, with some combination on x and y, right? And we have e as our main functions. So if we take the sine x cosine y as a power of e, so if we take this, so then we will have e with power of -1 and e with power of 1, okay? Which means that this e will be a constant. So if we take this as our m, so let the m is e with power of -1 and the capital M is e. And using the property for and let the area of D is a center, a disk with a center, it's basically a circle with radius 2, okay? So if you see this, so this will be the area. And the radius is r is 2. So area basically pi or 4 pi, okay, 4 pi units. I can write here, this area will be 4 pi. So
using the property, so m so we might have some conclusion here. So 4 pi over e less equal our function less equal 4 pi e. Okay. So we can estimate that this value is between these two numbers. Of course, the more narrow you have, like for example, if we have the m, the small m and the capital M, the more narrow, we could use the better approach, and perhaps we can deal with some errors. Okay, that's the property of the double integrals. Okay, now I would like to move it to a bit of new topics, just for a small introduction. And I will review again the double integral next week with some other questions and perhaps exercise. Okay, so the next thing is we can have the double integral in polar, in polar coordinates, which means usually you have the dx dy or dy dx. Now we are going to have the dr and d theta, and how to convert the usual or regular double integrals into polar. So basically you start by looking at this, and basically I think you are able to analyze the x and y component easily, right? So I think this should be very important. So first thing is we can convert this. Wait. Okay, wait. Okay, wait a minute. Suddenly my Apple Pencil doesn't work. Okay, wait. I don't know why it doesn't work. Oh, now it's work. Okay. So this will be x r cosine theta, y is r sine theta, and x squared plus y squared is equal to r squared. Okay, we just need this to convert xy Cartesian into a polar curve. Okay. Like for example, here we have two curves. Okay, we have a circle. There's a circle with radius 1. So x squared plus y squared is 1. Okay, and based on polar, which we learned at the early semester, polar will be, we have only two components, okay? The radius and the angle. So if we see this, I believe we can see that the radius is 1. I think it's pretty obvious, pretty clear. And since it's all solid, so it's move around all the rotations, right? So from 0 to 2 pi, so the full circle.
So we can say the 0 to 1 for radius and 0 to 2 pi for the theta. Now if we have this, what will be? So we have, for example, we have the circle here, which is radius 1. We have the second circle, which is radius 2. But this is actually a semicircle. It's not a full circle. So because it's semicircle, we are going to state this is the radius, the angle 0, and then we move pi. So we can state the radius. It starts from 1 to 2. It's not from 0, okay? Because 0 we don't need, and it has hollow. So 0 to 2, and theta is from 0 to 1. Okay, so that's how we describe the visuals and then define all the radius and theta. Okay, so that's for starter. And now we can have a what we call as a polar rectangle, in which, if you see this picture, this is our polar rectangle. So polar rectangle means we have this kind of profile. We have two different radius, A and B. We have two different angles. So first is angle here, alpha. And then the second one is angle from 0 to beta. So beta is here, alpha is there. So this section, or we call it sector, is start from alpha to beta for the angle. Okay, this is a region R. Okay? And we can write the region R. We can write the region R in terms of R theta. So radius is from A to B, and theta is from alpha to beta. Okay. Now, similar what we have in the introduction of double integral, we're going to slice. We cut like a webbings, like a spider webbings, okay, like in Spider-Man. So we cut this, and there will be a small pieces, right? And every time we cut this is when we are actually trying to emphasize the small things, and then later we are going to accumulate those small things, and that's what it means to be integrated. So integration is we cut everything into smallest particle possible, and then we condense all together, and then we sum or we add all of it. It's like when we think about so why integral or calculus matters? Because everything that you have learned from, perhaps if you think on physics or chemistry, if we don't have really much tools to solve the equation, or perhaps to visualize the equation, to describe what happened in perhaps in the phenomenon in physics or in chemistry, then we will have much trouble, okay? Because if you cut down like all possible matters that we see, like for example, because our world is based on what we call Platonic solids or Euclidean. Okay? So basically, Euclidean is what physics is based on, and basically that is the one that gives energy to classical physics, like a Newton's law and so on and so forth. But when we learn about quantum, there is a gap that is, we need to bridge that gap, because everything in classical physics, it doesn't work in quantum, right? Because quantum deals with the energy being a matter and wave at the same time, if you understand what I mean. Because energy is a wave, and because the matter is also like if we understand light can be wave, right? Like the double slit experiment in physics. Okay. So if you see any straight line, for example, like this shape. Okay, it seems straight, right? It seems straight. But if I propose that the straight line is actually illusion, do you accept or not? That straight line. A straight line here. All straight line. If you draw using your iPad has a resolution, right? We call the pixels. Like how much we condense the picture. Like the more, when we zoom in, if we still can see the square particles, it means that it's not good resolutions, right? But when we zoom in, it's still pretty clear. Like maybe when you deal with the factor illustration, when you zoom in, it's still clear curves. But if you maybe convert into PNG or GPG, if you understand if you're a designer, if you're dealing with design, those vectors convert into these pixelated arcs, right? If you zoom in, you see the pixels. So this line, we are not sure if that is true straight line or not, because perhaps our world here is basically just conjugation of the wave that is being condensed, if you understand what I mean. So you know the E is mc squared, right? So mass and light is a wave. So wave and matters can collide, and perhaps why the world is there is because we have so much energy. It has some frequency, so energy has a frequency, and then it can move around like in a way. It can vibrate, and it can perhaps condense and makes matter. That's how all the matters comes to. Perhaps also our life can be. So if you think that this chair is silent, no. This matter, if you look at the quantum level, is always vibrating. Your body is always in vibrations. We have natural frequency. So all the things in the world, it has frequency. Although we see that it's silent, it's still, it doesn't move away. Okay, that is your eyes that see it that way. But if you're going to go inside, we have the frequency. Even in our biology, in our biological world, there is vibrations everywhere. So there is nothing that is really silent, or if you think that way, everything is like having some frequency. Okay. So anyway, too far away from calculus. Okay. Anyway, go back to here. So we cut away this double or polar rectangle, and we cut into sub rectangles. So I think we can describe this small r as the Rij, this one here. So the Rij we can let's just define the r. The previous r is ri minus 1, and then the after that is ri. Okay, so let's define between these two lines or two radius. Okay, and then the theta will be this theta j and theta j minus 1. Okay, so that is for the theta. So j means the second axis.
or in this case, the theta. And then suppose that, so we let Ri asterisk, this will be defined as, so this is our assumption and our definition. This will be the average of these two radius, and the theta j asterisk, this is also the average for the angle. Okay. So then the delta, if we would like to compute the area, for the small area, we call that area as delta AI. So this will be half Ri, and the theta will be delta theta. Okay. Oh, this is squared, forgot. Okay, and then minus the second R, which is I minus 1 squared, and then the same delta theta. Okay. So this will be and we can split this using algebra. And the other one will be plus. And using the definition that we set up from the Ri asterisk and the theta j, we can make up this as Ri asterisk delta R and delta theta. So this is delta R, this is Ri asterisk, this is delta theta. Okay, so this is a delta A. So the typical Riemann sum, let me write here. So typical Riemann in double integrals of polar, we are going to have M, and then we have the second sum for the second axis, which is J, and this will be supposed to be XY, but I will change this X using the polar conversion. Or maybe let me just describe A area directly. Becomes R, and then delta R, delta theta. Okay. So if you see the structure, there will be a little bit differences from the double integrals in regular. So we have some additional R here. Okay. Okay. So from this part, we can, if we can write another function g to change this f. So f is the counterpart for our xy, or g is the counterpart that we are going to use that in our polar. So we can start to write in terms of g. The asterisk means it's a sample point. You could pinpoint in any place in the region. Okay, that's what that means. Okay, let me finish this. This will be equal to the double integral. So g r theta, this will be dr d theta from a b alpha beta. Okay, but it is in terms g. If you want to put back the idea, which is start from xy, we can write this. If you want to change into g, we can. But it's better to use the f, the original functions. This is f, and change the component into polar. But when you have the structure of f, don't forget, it's not only dr d theta, this will be having r, dr d theta. Okay, so there will be additional r here. Okay, I think we can have a break. I'm not sure whether we can finish all the questions, but I would like to add more. So let's start with this, and I think finding local max, local mean, and saddle point. My expectation, the part A should be, most of you need to be able to get it. Okay. If you still have a struggling finding for the part A, then you need to make more practice. Okay. So basically, how to find the local maximum, minimum, or saddle point. So first, we need to find all the possible points. Okay. We call the critical points. So that's the first idea. So first, we need to find the critical points. So how do we figure out which one is the critical points? Since this is a function of two variables, there are two possible ways. First one is partial x is 0. The second one, partial y is 0. Solve this system, you get the points, or you can get some possible scenario of the points, and then you get all the xy. You can have 2 points, you can have 3, 4, and all those points basically we need to check. Okay? We need to check whether they are going to be local max, mean, or saddle point. Okay, I think we can try. So partial x we can get through partially derived with respect to x. So we have 6x minus 6x squared. Or we can take this as 1 minus x. Okay, so this will be equal to 0. So from the partial x, we get possibility that is x is either 0 or x is equal 1. Okay, so we have two possibility. Okay. Now we get the other part is partial y is 0. So first is we derive this partially. So this will be 3 minus 3y squared. And let this become 0. So that's equal to 0. So y squared is equal 1, or y can be equal 1, or y can be negative 1. So from this 4, or from this 4 numbers or 4 values, we can have some possibilities. Okay? So we can make out the critical points, that is x is 0 and y is 1. X is 0, y is -1. X is 1, y is 1, and the other one is -1. So we can have this sort of critical points. So we get critical points. Next is we need to test the critical points. Okay, so test the critical points. Okay, my suggestion, you can prepare a table. Okay, so your notes can be easily understandable. Okay, and then test all the possible points here. So let's say this is critical points. Let's say this is 0, 1. And then we are going to use the second derivative test, which sometimes we name as the D. So D is basically partial xx, partial yy, minus partial xy squared. Okay. And what we need in D is not the value, but the sign, okay, with whether it will be positive or negative. Okay, so no need to compute the number. Okay, so maybe before we continue, we can prepare the second partials. Okay, so the second partials we can get from, for example, partial xx is 6 minus 12x, right? And then partial yy is negative 6y. And then partial xy. Actually, you can use partial yx, but because they are the same, I will just use xy. Xy, because there is no y in the equation, so I will take this as 0. Okay, and then we can start substitute the number inside the equations. Okay. So x is 0, y is 1. So substitute, basically we substitute to have partial xx. So this will be 1. So 12, 6 minus 12 is negative. Right? So it's negative. So we can, perhaps if you are doing it digitally, you can maybe write this negative just to note the signs. And then partial yy, so only y is 1. So it's negative again. So negative, negative become positive. So we have a positive here. And because the x, y is 0, so we only care about this, right? So the d is positive. So when d is positive, we have two possibilities. It's either local max or local min. Okay? So how do we know which one is max and min? We need to test the partial xx or partial y. But I think just test the partial xx should be sufficient. So we need to test the partial xx. So we get this one is positive for d. Partial xx, we take x equals 0. It is positive. So when it's positive, it's local minimum. So this is positive. So it's local minimum. Okay. And then test another one. Do the same thing. So negative 1, put here is positive 18, right? Positive 18. That will be 0. Oh, 0, sorry. 0 is positive. Let me write positive. So this one positive. YY is oh, wait. I did it wrong. This is supposed to be positive here. This is not positive, right? So if we have 1, it will be negative, right? It will be negative. So it should be negative. So when it's negative, then this decided to be saddle point. Okay. So it's positive here. This is local min. Okay. I mix up between these two. Okay. Okay, now this is correct. Okay, the other part is we can take 1, 1. It's negative and negative. So positive. This is negative, so this will be local max. And try the other point. You can check whether my table is correct or no. So take another one, it's negative. It's positive, so it's negative. So it's already negative one more time. We get directly this is the saddle point. So we have these 4 critical points, and we have determined all the extreme property. Okay. Local minimum, maximum, or saddle point. Okay. So this is only part A. Okay. So this is part A. The part B, we have additional boundary. Okay. So what is the boundary? Boundary is a triangle that is based on those vertices, -2, 2, 2, 2, 2, -2. If you want, you can try to draw. I think would be better. Will be more accurate. So perhaps this is the D. Okay, we can draw the point. Okay, suppose that we have 2 is here, -2 is there. This is another -2, -2. So we have 2, 2, this one. We have -2, 2, this one. And last one is here. Okay. Okay, that will be. Okay, so we have this triangle. We can start from when, so let me write here the equations so that we can focus on 1 plus 3x squared minus 2x cubed plus 3y minus y cubed. Okay. Okay, now we can start with the y is a constant. Okay, so we can start on, so y is a constant 2, and x will be going from -2 to 2, right? So x is variable, y is constant. We can write the system, a new function, and take the y equal to inside. Okay. Okay, so 1 plus 3x squared minus 2x cubed. And then this will be 6 minus 8, right? So -2. Maybe to make it easy, I will take the new function as g. Okay. So g of x, let me write as this. And to find the max and mean, we can take the first derivative of this and write down that we can have 1 minus x. So we can have x 0 and x is 1. So this is the one that is locally will be the extreme value that we can try. So what is this about? So based on all the points that is possible, we could try the 0, 2, 1, 2, and try to evaluate the value, and also try, because we have the negative 2 and 2, we can also try that as well. So we can try all the possible value, and also try the endpoints. Okay? And then we can check. So this is this line, okay? And then we check the other line, and also these lines here. Okay. I think this is not in the center. Let me make it center. Okay. Okay. Now we can check the F02, which is negative 1, right? And F12. 1 plus 3 is 4. 4 minus 2 is 2. Minus 2 is 0. So 0. Okay. And then try also the negative 2, 2. Can someone help me? What is this?
Quite lazy to compute. Minus 2 is 4, 12, 13. 16 minus 13 is 3. 3 minus 2 is 1, right? It's 1.
I think we need more space. But I think I have done this. I think I will skip some parts. Okay, I will go directly to the answer. So this will be what 12, 13. This is negative 5, right? This is for this one. So this is for, let me write, this is 1. Okay. So you need to do all the possible lines. Okay. So this is only for 1. And you need to make the other line, this line 2. We can start by taking x is a constant and y is the variable, which means that you are going to input 2 into the equation, and you will get the equation with variable y only. And do the same thing. You're going to have the derivative, the first derivative, and then take it equal 0, just like normal calculus 1 max min value. You get the points, and you check the points, all possible points. Possible points from the extreme value, possible points from the endpoints. Okay. So all the 1, 2, 3, check all the points. The one that is maximum will be the absolute maximum. One is minimum, absolute minimum. Okay. Let me skip some process and give you the final answer. Okay. I will show you the process here. Okay. Okay. Here. Okay. Oh, it's actually 27. Oh, I make a mistake in the script. It should be 27. Okay. So this is the when y is constant. Okay. So we have this, and then the second one is for x is constant. So let me write here. This is oh, I'm making also a mistake. This is not correct. This is x is constant. So this is 1, 2, 3. Okay. So this is, yeah. Okay. This is already correct calculations, but I make a mistake here, and also here. This is not 1. should be 27. Okay. Okay, I already rechecked this for many times. So I'm confident this is correct. Okay, so this is 1, and then 2 is the x equal 2, and then 3 is the y equal minus x, or x plus y equals 0. So this is the first one. The second one is for x is constant. Input x inside the formula, okay, and then y is variable. And then taking that into rename a new function g2, and then make the same method, and we have this equals 0. Y will be plus minus 1, and then this y with the same x equal 2, we are going to test 2, 1, we test and it's negative 1, 2, negative 1 is negative 5. Okay. And then the endpoints also check. 2, negative 2 is negative 1. Okay. And then you can also check the third line using the y equal negative x, which means we have x and negative x, and basically substitute becomes x. Okay. And then we have another g3. This is just my way to rename the function to get easy for next step. We get the minimum maximum problem again. Take the first derivative equal to 0. We have this, and then where's the rest? Okay, so we get this is x minus 1 squared, which is x is equal 1. So there's only one extreme point, x equal 1. So 1 and negative 1, so x minus x, right? So 1, negative 1, we check the result is 0, and the rest will be the same because we have done this, so they are also have the same. So we have 27 as our max, and negative 5 as our minimum, right? So these 2 points, they are the same, 2, negative 1, and 2, 2, they have the same negative 5. Okay. The question, the previous question, the first question should be also okay, and I think it could be easily understandable because it's a rectangle. Rectangle, I think you can check for every line when x is constant and then y variable and y is constant with different constant. So we have 4 lines for rectangle. Do the same thing with the previous one. Okay. Basically, the part A will be the same. Critical points. So you can get the partial equals 0 for each one of x and y. Partial x equals 0, partial y equals 0. Solve the equations, get the points, test the points using the second derivative test, and then get the local mean, max, or saddle points. Okay. So that's basically the steps. Okay. I think I need to go for other questions. Okay? So these 2 questions very similar, very I think same procedure. Okay. I hope you get the procedural. The next one will be how about this one? Okay. This is also max min value. But this is having this constraint, which I think this will be using Lagrange. Okay? Using Lagrange. So maximum value of f x y z x squared y z plus 1
But we have intersection, z equal 1. Intersection is z equal 1. We have also a constraint that is a sphere. So the surface is cut by z equal 1. And also they are going to be in sphere. So the sphere will be going around. So they want to compute. So the question is asking the surface with this boundary z equal 1 and the sphere, what will be the possible maximum value? So this could be
solved by taking the, so when z is 1, first is the functions become x squared y plus 1, okay? And let's say this is going to be just a function, two variables. Okay, let's say this has become the fxy. Let's rename a new function. And then when z equal 1, we can also have that this will be 9, okay? Will be a circle, okay? Which means the sphere, so we have a sphere, and at z equal 1, we cut, and if we see from the top, it's a circle that is x squared plus y squared equal to 9. So it's actually like you have the, let's say this is a ball. And then this is 1, okay? And you are going to cut this, okay?
Precisely at this z equal 1. And then if you use the top view, you see from the top, you get this circle. Okay? And then basically we have this new constraint, new function. This is the one that we need to maximize using the Lagrange. Okay? So take Lagrange, then we can let another function, let's say g, a constant it doesn't matter, but I will just put this minus 9, okay? Because if we take partials, basically both x and y, the constant will be gone, right? So not really matter. So we can take the Lagrange, which is using the del. So the partial fx lambda partial x of g, this will be 2xy equal lambda, and g will be 2x, okay? And then for partial y, this will be x squared lambda, and then g partial g is what? 2y. Okay, we can simplify it a little bit. So this will be xy, 2 lambda x. And this will be x squared, 2 lambda y. Okay, now what will happen? Now we need to think in this Lagrange. Sometimes we are going to have some like several system of equations. And sometimes we need to set some assumption. So maybe there will be some cases that might happen. For example, if x is 0, what will happen with the y? And if lambda is 0, what would happen? Okay.
How much time we have left? Okay, I think I need to take the final results, okay? So let me give you final results, okay? Some of the cases.
So we can have x equals 0, and lambda is not 0. So that is case 1. So if lambda is not 0, then y is also 0. Okay? But then, if we take into our g is this one here, that's 0, 0. This will be equal to negative 9, which is not 0. Okay? And then the second case is if x is 0 and lambda is 0. So we have both x and lambda is 0. So if this is 0 and lambda 0, then using this part here, when x is 0, y squared could be 9. Y squared could be 9. So this 0, 0, and this will be not 0, which is, it could be 9, or plus minus 3, or 1. So we could have this point, okay, which is both, because of the square, will be the same value. So 0, 3, 1, or 0, negative 3, 1. Okay? And we can compute that. Okay? Now the third case, the third possibility, if the x is not 0. X is not 0, y equal lambda. Okay? So if x is not 0, so basically we can cancel this, which is give you the idea that y could be the lambda, right? Y itself could be lambda. When y is lambda, then we could turn into this equations. When y is lambda, then the x will be so since this is lambda, the x will be lambda squared, 2 lambda squared. X squared will be 2 lambda squared. So x squared, substitute here the x squared, and this is y squared. We could get the lambda. Okay, we could get the lambda, which is plus minus 3. So let me go through plus minus square root of 3.
Okay.
Which then, this could lead into different points. Okay. So we have the first possible point is this.
The other possible points is that we can have
we could check this and then take this into the equations, because x is 2, where's x here? X is 2 lambda squared, so we can get into the equations. Y is the lambda, so y is square root of 3. So we could get the x, because it's from x squared, you can get plus minus square root of 6. So we could get these two values, and they'll be the same because of the square. So this value will be the same. So it will be 6 square root of 3 plus 1. Okay. And the second possible root that we might have is the negative 1. The negative 1, because from the equations, the y will be, where's my, let me write again the equations.
equation is this from here, x squared y plus 1. Okay. Let me write here. Okay.
So we can input these two, and becomes this. You can input this, become this, and from the possible value that we have, we can see that this will be the maximum value. This will be the minimum value for the left. Okay. So solving Lagrange, sometimes we need to use some cases, because there will be many possible paths that we could choose.
Okay.
The second question here is also Lagrange. You can try this as well. But it's interesting. It's ln, 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 logarithm. So it will be 1 over 1 over 1 over something. Right? And then you are going to equaling that to the Lagrange of this. So 2x to y to z. So you will have 3 equations, right? 3 equations for this one. And solve simultaneously, either substitutions or either using some basic definitions from the equation itself.
Okay. maybe one more last question. Okay. So the first one is max min value in partials. The second type is the Lagrange. The third type is this. Okay.
So we have z to the power of 5 sine x z cubed plus y z equals 4. Find equation of the tangent plane at 0, 3, 1, and then you have the second question, which is giving you the definitions. It is implicitly near, so it has zxy, which is a function of two variables of z. It is implicitly near 0, 3, 1. And then we need to find that the partial z with respect to x and y on those points. And basically all this question, they will be all related, especially the last two. So after you get the partial, the last one is basically the linear approximation, which is basically the tangent plane, okay? The tangent plane formula. It's very similar to tangent plane formula. And then we are going to use to approximate the real root of this polynomial. And how to get this, I think we can
start one by one. Or I have done this previously. So I think let me give you directly so that we can have more time to think. So first is, we could define the function and name a function. Okay? I will name the function as the capital F. So this is our function, right? And then we can take the del F, meaning partial x, partial y, and then partial z. Okay, so partial x, so this is no x, so only here, right? So we have only the cosine x and z cubed. And partial y, there is only the last part for y, so it's only z. And then partial z is all over the place, right? So 5z to the power of 4, 3 sine x, and then the z cubed become 3z squared, so 3z squared, and then the last one is plus y. Okay? And then take the points, put inside, and then the tangent plane will be the del f at this point, multiply the points, the initial points. Initial point will be x minus 0, y minus 3, z minus 1. So we can dot this too. So 1 with x, 1 with 1 minus 3, and then add all together. So we get this tangent plane. I think using the del and then dot with the point, I think it's pretty minimal compared with the. I think the equations, if we describe, this is going to be described as using the partial x, and then we take this x minus x0 plus partial y, y minus y0, and then plus partial z, z minus z0 equals 0. So this is the same equation.
But I'm using the del and dot product to make it compact. So we get the tangent plane, and then the second part is the
partial techniques. So using the implicit.
Now implicit means in calculus 1 we say implicit if, so we have y, we have x in one equation, and we define that y is actually a function of x. Okay, that's in calculus 1. In calculus 2, we may have three variables. Okay. So we have x, y, z. So one of the x, y, z, it will be a function of another two variables. For example, in this case is z. is function of xy, which means z will be implicitly can be defined inside the equations.
So the short one, if we take the
Partial z partial x at this point, we could use this formula. I think I have given this a couple weeks ago. And basically we just take this 0, 3, 1, take into the partial axis
over up there, here.
So this is partial x, so this is,
I think I will write down so that you are able to see this partial x, partial y, partial z. Okay.
so take 0, 3, 1 into the equations. Remember 0, because sine x is 0, so 0, so we have only 5 plus 3. 5 plus 3 is 8. Okay, so this will be 8. And for x is 1, and then, yeah, it's 1. So 1, so negative 1 over 8. So we can do that.
Or another alternative is basically direct approach. Okay, we can approach directly.
Taking the partial with respect to x for this equation. But we need to know the definition first. Okay? Because z is function to variables. When we apply z with respect to x, when we apply the partial, we can derive, but we add the partial z partial x. Okay? And do the same thing with this one. Because this is x, which is we need to derive, z also can be derived, so we need to take product rule. Okay? So take product rule, this is the product rule, okay? And every time we derive the z, don't forget to multiply this. Okay? And then we have the last one, we only need to derive z. Okay? Y is we can consider as a constant. And then we can input the 0, 3, 1 here, because I believe it will make it easier. So when you, maybe in exam, okay, you are doing this, you prefer to simplify first. Maybe it will take time, it will waste your time. My suggestion is just take the point first, because sometimes the question will make it simplified. For example, when x is 0, some of this will be 0. So for this one, it's become 0, right? So we don't need to worry about this much, because this will be 0 because x is 0 here. Cosine 0 is 1, so z cubed is 1. So we can compute everything, and then we can have this. And then we can solve this equal to 0, and we get negative 1 over 8. So either way, you get the same result. Either way, you get the same result. But you need to make sure you don't make mistake when you partially derive. Okay? Or you can take the shortcut using the fx over fz, okay, minus. But if you also forget, you can draw the diagram. Okay, draw the diagram. So the diagram, draw the diagram first. F x, y, z, and then this is also x, y. Okay, and then define the partial by this way. You will get the final result is the same as this. Okay? And do the same thing with this. You can also do the same thing with using this one, but with y. I think much more simpler, because y is not as much as x here. It's only here, y. So I think should be very very direct. Okay. We still have another part, right? Which one is the last one? The linear approximation. Linear approximation. Okay. Now we have this function here. Function p of z is z with power of 5, 2.9 z minus 4. If you see, and then if you take some points, we could get this
if we have x equals 0 or and y is 2.9, if we put into the equations. So if we put here x equals 0 and then y equal 2.9, we will get the function that we want from here. So the approximations, if we have the linearizations, what we do is basically we are going to input this at the end. So let me write here. So the linear approximation near the point 031, okay, which we can use this 0 and 3 in our linear linearization. So linearization is actually tangent plane. Okay, if you see the form, this is actually similar from this. Okay, so it's actually very similar to what we have in the tangent plane. So we are going to take the z as the L, the one that we want to find, and then the FAB is actually when we input 0 and 3 to our function, that will be the value. And then plus the partial x, and then x minus a we can take equals 0, partial y minus b equals 3. So we can input all together. All the partial x and partial y we have done in the implicit differentiation, which is negative 1 over 8. So we can input negative 1 over 8 here. X is 0, okay, y is 0 here, and then this will be y minus 3. FAB is z, this one over there, right? So 1. So this is the linearization, the approximation. Okay, now to get this p from the functions, we can input x equals 0 and y equal 2.9. So then we can approximate by taking the 0 and 2.9 inside of the linear function, which we get is about 81 over 82. So it's quite challenging and interesting. I believe it's challenging, right? I'm preparing something like this, but not that challenging. Okay? But like from one function, it could be like multiple questions. So you can correlate with all the techniques you learn in partial. They are all connected. So if you learn one segment, you need to learn other segment as well. If you are missing out something in between, there's a high chances that you are not able to solve all the examples. So you need to connect all the dots between the segments in the partials and everything in calculus. If you miss out, for example, you need something from calculus 1, then you might not be able to solve the whole thing. Okay. Okay, I will give the notes so you can review, and perhaps maybe not more. I think you can just take more exercise from the regular practice, okay, just to make sure that you are able to solve. Okay. Especially the max min value or Lagrange, at least that will be appear. Okay, max min value and or Lagrange. Okay.